Hey, today's talk is from Michael Valore of Westinghouse Nuclear. Michael is currently Senior Director of Advanced Reactor Commercialization at Westinghouse and is responsible for leading the effort to bring eVinci to the commercial market. Prior to this role, he's served in a senior position in Westinghouse America's procurement and was responsible for the North American supply chain, and has also managed projects for AP1000 in the US and China. Mike will be talking today about the eVinci Microreactor, and I know we're all enthusiastic to learn more. So thank you for joining us today, Mike, and look forward to learning more.
Thank you for having me today. So I guess we can get right into it. So let me share screen. I presume that's working. Okay. Okay, great. So you can hear me and you can see the screen? Okay, great. All right, so I represent Westinghouse Electric Company, as Ben mentioned. We are the Westinghouse nuclear organization that draws its lineage back to the original Westinghouse. We are not affiliated with any of the Westinghouses that make appliances and televisions and those types of things. Those Westinghouses actually, they pay CBS a license fee to be able to use the Westinghouse name. They didn't grow up with, most of them did not grow up with Westinghouse, but we take our lineage back to the original Westinghouse. We have delivered nearly half of the world's nuclear fleet, including the technology for the PWRs in the United States, France, Korea, and Japan. We were the organization that developed the technology behind the nuclear navy, both from the submarine and aircraft carrier perspective. And we have about 9,000 employees across about 19 countries. So quite large organization, but we have been focused on servicing the nuclear fleets from a fuel perspective, a services perspective, as well as developing new reactors like the AP1000 and the eVinci, which I'll talk about today. So the eVinci microreactor, just at a high level, it's really like a nuclear battery. It's charged up with nuclear fuel, and it can be discharged in the form of heat for many different uses. The net electric power output is approximately 4.5 megawatts. One of the things that's greatly different about this design is its transportability, and I'll talk a bit about that today and why that's a critical characteristic. We are cost competitive with our first-of-a-kind units. Through a lot of detailed analysis, we've been able to determine that we can enter the market, even with our high first-of-a-kind costs in areas where diesel's being shipped for electricity and heating. So we see a very easy entry point into the market for this product, even at the first-of-a-kind unit costs. We see minimal on-site personnel needed. Realistically, this reactor will run itself. However, from a regulatory perspective, we will likely need an on-site operator and potentially also a security individual on staff at the location. But our goal is, over the long term, for this to be a completely autonomous technology. I'll show a bit today. We've been maturing the design and the manufacturing of our pieces and parts for the reactor, doing quite a bit of testing and ensuring we're ready to proceed into the regulatory process. And what can we do with the reactor? I'll talk a bit today, but we can make heat, we can make electricity, we can load follow at millisecond type ranges if needed. And that was a key characteristic of our technology, such that we could operate pairing with renewables or even individually in an off-grid situation. So really what's different about this technology, including other microreactors, is its portability. So our goal is to be able to deliver the entire plant in 4 truckload-sized containers. The largest would be the reactor container itself, weighing about 120,000 kilograms, about 40-foot long container by 14 by 14 foot. And then from there, the power conversion unit It's quite a bit lighter and smaller, and then an instrument and controls cabinet container, and then miscellaneous support equipment that would be tailored to the actual use case. So for instance, a heat exchanger, if we're capturing the waste heat from the power conversion system for district heating applications, just as an example. There's many advantages of having a transport reactor. One is certainly that the weight and sizes allow for deployment in remote areas. That's where we see the entry market for this technology due to the very high energy costs in some remote areas. It also allows for scaling to meet the demand. So, many industrial sites and even communities, their energy demands will grow. And then potentially for a mining site, for instance, their energy demand wanes over time as the resources at the mine site have been captured. So the transportability allows for us to bring more reactors or remove reactors to scale with that demand. Another key advantage is that we don't need to store the spent fuel or the waste on site. When the reactor's reached its refueling point, which is basically a 4 to 5 year time frame, we remove it off from the site for that activity. If it's reached its full life, we also remove it from the site, so there's no waste storage. This greatly supports the ability for decommissioning as well, for sites to be able to return to greenfield. This is very important because many of our deployment areas in those remote areas are environmentally sensitive places where a mine site or even a community would want to return the land back to its natural state after use. The biggest advantage I see for the transportability is that it minimizes the construction cost and labor. So as Ben mentioned, I'm a veteran of our AP1000 sites. At one point I was responsible for delivering all of the material and equipment to those sites. And I can say firsthand that I did not worry about delivering the nuclear steam supply equipment. The real challenge that we had on those projects was delivering the construction materials and keeping up with the site when things would be damaged or design would be changed or an issue would be run into on the site that was unexpected. There was just a constant difficulty of delivering and construction materials and keeping the construction site running. The major equipment was really not the critical path on, especially the US projects. So, the transportability of this really allows for above ground installation, which is important in remote areas, so we don't have to dig into the permafrost. It reduces the construction time and labor, which is important again for remote areas because a large construction force that's trained to nuclear quality standards would be quite difficult and expensive to deploy in some of these areas. Our goal is to actually bring the reactor on site, have it installed and operate it in less than 30 days. So truly more of a diesel generator type technology without the emissions and the noise. Prospective markets for this technology, as I mentioned, remote mining is an interesting one for us. There's multiple remote mining sites in Canada that, and one or two in Alaska, that their energy output or their energy needs could be supported by eVinci's output or multiple eVincis. The mining sites also have heating needs, which we can capture the waste heat from our power conversion to supply all of that heat. We've been looking at some industrial process heat applications. We can put out temperatures as high as 700 degrees C with this reactor. So there's quite a bit of interest in what we can do with those high temperatures, and also our ability to generate those temperatures without emissions, we see as a key advantage for us. District heating we see is basically any heating. There's very few options for non-emitting heat generation, and nuclear reactors obviously are very efficient at making heat, so district heating is interesting to us as well. And then for remote communities, we see a combination of both electrical district heat applications as well as potentially bringing in hydrogen generation, solid oxide electrolysis, like high temperature hydrogen technologies that could actually support decentralization of the hydrogen economy. We see marine shipping as a potential market for this technology, even though we'll have some work to do to be able to deploy it, but its size, it could really support marine shipping. Air Force and other critical infrastructure could be very interesting to us. You know, there's a high interest from the military from the perspective of getting Air Force and other military bases off of the grid and off of the reliance for delivered diesel. And then even disaster relief, where we see ours as the only technology that we could bring into a site and have it operating in a short enough time period. The disaster relief could be an option for us. And then we also research reactors, which could be interesting from a perspective of working with the university, where we could supply electricity, heat, as well as provide a platform for research from a gamma ray and neutron bombardment perspective. So what can we do with it? As I've basically talked through, but just to put it in visualization, we can make high-grade heat over 700 degrees C. We can capture district heating type heat from the conversion system if we're making electricity. And then from an electrical perspective, we can pair with renewables, we can operate off grid, we can load follow again at almost millisecond ranges with this technology, which opens up a host of opportunity. And as mentioned, we've been looking at hydrogen pairing with us such that we could truly decarbonize entire communities or industrial facilities. You know, there may be areas where shipping and things like that transferring to battery electric could be very difficult. And also some of the areas where we're looking at deploying this technology, the temperatures could be so low at some instances that battery technology is not a wise choice. So hydrogen could be that path that we could literally decarbonize an entire island or community. We talk about environmental impacts. You know, there's been a lot of concern about, you know, what it could be the downside impacts from a nuclear reactor to the environment. And I really see it as what are the upsides to nuclear versus diesel. You know, basically, it's quite simple, but I think worth just hitting on. We are emissions free, no carbon, but there's also particulates such as PM2.5, PM10 that are being shown to be very dangerous to the public that diesel emits that our technology obviously does not. We eliminate risk of fuel spills or leaks. Many of these remote areas are getting diesel shipped in by either plane or truck or boat through, you know, quite environmentally sensitive areas. So spills and leaks are of great concern. Some of these towns, even the biggest things you can see in the town are actually their diesel storage tanks. Eliminating that diesel chain in some of these areas would open up great opportunities and reduce environmental risk. Minimal maintenance, we have very few moving parts on this technology. When we compare to diesel generators, they actually require frequent maintenance. They require machine rebuilds every 6 or 7 years, which can be quite difficult to do in some remote areas. We don't need any water for cooling, and I'll get into a bit of that. And we don't require any oil lubrication. And then reliability in all weather conditions and temperatures is a key aspect that we have. Diesel in some of these areas actually can get to the point where it's not a liquid any longer due to the low temperatures and becomes quite difficult to deal with. And then really we can capture our excess heat for a multitude of uses that right now are primarily being supported by diesel, propane, and other fossil fuel burning activities. But one eVinci, just to put some numbers around it, could eliminate greater than 31,000 metric tons of CO2 per year. Footprint, we are much smaller than equivalent renewables, especially when you consider the capacity factor of renewables. We have a near 100% capacity factor with this tech. The building, basically, its primary purpose is environmental and radiation shielding. So, radiation's not being emitted out into the public from the reactor. The building will provide the supplemental shielding needed. All of our construction, again, is above ground. And then you see the site footprint itself, including the fenced area, is less than an acre for a single unit eVinci, but a double celled building. And if you see in that photo in the lower left, you see there's 2 bays, and that's our building for situations where we would have one eVinci operating in one of the bays. Whenever it starts to get to the point where it needs refueled, we would bring an eVinci into the second bay, get it connected up and powered before we remove the first. So this is our single unit building for situations where we have to provide continuous energy output. There's other variations on the building, such as a single cell building where we could remove the reactor for refueling during periods of low energy demand. And obviously we can scale up even higher than one to much larger numbers of eVinci should the technology or the use require it. We've incorporated passive safety into this reactor. Westinghouse really pioneered that in the nuclear industry with our AP1000, which is substantially able to be shut down without any operator interaction and very little interaction after even the first 72 hours after an accident. This reactor, it takes those same principles and incorporates passive heat removal should the primary reactivity controls fail. It also relies on passive heat pipes, which to remove the heat from the core, which on a primary coolant basis, which I'll show how that works. We're not susceptible to loss of coolant accidents in the traditional sense. The actual fluid in the heat pipes is not pressurized. So, we don't have to worry about a high pressure pipe break in this technology. And basically, as mentioned, we don't see any operator action necessary. We're planning an operator from a regulatory perspective. The fuel, we're planning on Triso Fuel, which is basically a self-contained fuel where the uranium kernel is encapsulated by multiple high-strength materials, including silicon carbide and other layers, such that the fuel can actually resist temperatures of 1600 to 1800 degrees Celsius. It's basically close to, if not a meltdown proof fuel. So realistically, to put this technology in areas that are environmentally sensitive, or we're going to need to get the public comfortable with the technology. But we also know as a reactor designer that it has to truly be something that is a meltdown proof design, and that's what we will ensure before the reactor goes into commercial operation. So our reactor, as I mentioned, uses heat pipes for basically its reactor coolant system, a passive heat transport device. Imagine a small tube that's enclosed, it's closed on both ends and filled with sodium. So if you follow me on the diagram on the upper right, the left side of the heat pipe would be embedded into the core where the nuclear fuel is. And as heat is entering that side of the heat pipe, the sodium drives through the center pipe to the right, where the heat is captured by our primary heat exchanger for process use. And the sodium, as it travels up a wick on a microporous metal wick on the inner diameter of the tube, and it travels back to the left side. So the heat transfer is basically completely passive. There's no pump, there's no valves needed to remove the heat from the core. And they are self-regulating devices. So when more heat enters the left side, the reaction speeds up and more heat is removed from the core. So this is an area that Westinghouse has spent considerable time and investment in to develop and test this technology and also be able to manufacture it to nuclear quality standards. We actually scanned the public market for this type of heat pipe and weren't able to find a supplier that could meet the requirements we felt were necessary to supply to nuclear. So we developed it ourselves. So now we can make our own heat pipes and we can test them. And if you see in the lower right, that's one of our heat pipes being heated to 800 degrees C, where it performed flawlessly until we basically just stopped the test because it had gone over 120 days of runtime. So we have quite a bit of experience in manufacturing and testing these heat pipes at this point, and they're key to our reactor design. With any nuclear technology deployment, a new nuclear technology, there's a very rigorous testing program that has to take place. Westinghouse has quite a bit of expertise in this, and we've been building and testing components now for several years. But this photo is actually very recent, from last month, actually maybe the beginning of May actually, where we are performing a test similar to the one I just showed on the previous slide, but with a battery of heat pipes within a cell of our reactor. So if you imagine the reactor core is a group of hexagons like a honeybee nest. One of those hexagons we call a cell, and it has 7 heat pipes in it, which you can see in the upper right. And we are heating those with electric heaters. We're not using nuclear fuel yet in this test, but this test will show that a battery of heat pipes will function as a unit. It'll give us information about how the temperature disperses through the core, and also give us some insights into the performance of our primary heat exchanger. So we're calling this our unit cell electrical demonstration test using Westinghouse manufactured heat pipes, and this will be going now for multiple months. We will be running normal operation scenarios, startup, shutdown scenarios, as well as transients on these heat pipes. So just to summarize, from a safety perspective, it's truly a walk-away safe, more like a battery technology. From a reliability perspective, we have been doing great amounts of manufacturing and testing of components. If you look on the right, you can see a graphite core that we had manufactured to ensure we could actually meet the tolerances and the requirements we would need for this reactor. It has very minimal moving parts. Every time we look at adding a moving component to the entire train, including the power conversion system, we take it very seriously because, again, we want this technology to be able to be sat in a remote area, turned on, and basically ignored until it needs to be refueled. Cost is competitive from an LCOE perspective on our first-of-a-kind units with transported diesel. And then, key to it truly is that minimal construction cost. Nuclear in general, I think we tend to underestimate the construction costs. And I believe that many of the reactor designers that are working on new technologies right now will inevitably underestimate that construction cost. So again, our choice was to remove it almost completely. So there will be some building construction, as you saw, that we will have a small building, but none of that building will be safety related, which is very important. And when we look at a timing perspective, in 2021, we're performing that electrical demonstration test of the photos that I showed. In late 22 to early 23, we'll be performing a similar test using actual nuclear fuel at Idaho National Labs and Los Alamos National Lab. And then really from there, it's finalizing the full-size reactor design, building the components, and driving to a full-size nuclear demonstration, likely that would be placed at one of the U.S. national labs out in 2025. From there, we see first commercial unit deliveries in late 2026 for eVinci. That's a blink of an eye for a nuclear development timeline. But the work that we've done to lay the groundwork and ensure we can actually make these parts and build them and test them is absolutely critical to a nuclear development. And we've really been laying the groundwork for that effort. We'll be engaging now with the regulators in the pre-licensing processes in both the US and Canada by Q3 this year, where in Canada we'll be starting the vendor design review process there formally. And then in the US, we're working with the US NRC even now on our licensing approach and strategy. So that's what I had for today's presentation. I wanted to leave plenty of time for questions, and I've brought one of our leading technical folks from Westinghouse as well to help me out with the question and answer session.
Thank you very much, Michael. That was a really interesting introduction to eVinci, and it's really promising that you can see these markets where it can be financially competitive. If I can just kick things off with a question, how do you handle things like earthquake proofing, or is your source term low enough that you don't have to worry about earthquake proofing?
Yeah, so from a seismic perspective, there will be seismic isolators designed into the transport container for eVinci. That's actually one of the keys to ensuring we don't need a safety-related seismic structure. The simplicity and the size of the reactor, as well as the shipping container robustness that will be required to actually meet US NRC transportation requirements, also help to support our case that we can keep that structure a non-safety related structure.
Okay, that makes sense. Thank you. Are there other questions from the audience?
Yeah, so Mike, thanks a lot for your impressive presentation. So can I ask what's the limit operation temperature of this design?
So the design temperature is 800 degrees C for the reactor core. Operation or output temperature, again, that we could capture, around 700 degrees C. The Triso Fuel could, is safe up to temperatures of 1600 to 1800 degrees C. But realistically, our design basis for the core is around an 800 degree C operating temperature.
Okay, thank you. And another quick question is, what do you think is the limitation of the heat transfer coefficient? So for example, do you think a higher efficiency heat pipe technology could help improve the design or something like that?
Not sure I quite understood that question on the what would the limiting factor be. Could you repeat that one?
Okay, I apologize. So I'm asking, so for example, in normal operation, it's everything works well, but for example, if it's in accident conditions, there might be a stronger heat stress to the structure, and at this moment, each of the existing heat pipe might have to transfer more energy comparing with normal operation conditions. So what do you think, what kinds of technology do you think might be more helpful and might be more important, like a stronger heat pipe which potentially can transfer more energy into this in this situation will help? Or do you think that any other consideration or technologies could help?
Yeah, so in an accident scenario, really our biggest fallback is the passive core cooling jacket and system that would keep the reactor below, certainly fuel failure temperatures through natural circulation of air or other medium. So, step back here. So, if you see in the photos on the left, that's our passive core cooling jacket, which through natural circulation will drive air across the container surface to remove heat from the core in an instance where we're really at an accident type scenario.
Okay, thank you.
We have a question in our chat, which is, what is the power conversion technology to be used?
It's an open air Brayton cycle system. Basically high temperature air jet engine type technology. It's pretty good efficiencies at the types of temperatures that we're outputting. It's also higher technology readiness level than supercritical CO2, for instance, also lower cost of operation than supercritical CO2.
And is there a direct heat exchanger between the sodium heat pipes and the supercritical Brayton, or do you have an intermediate loop?
So the primary heat exchanger would capture the heat from the heat pipes, which is integral to the reactor core. But there are applications for district heating or industrial process heats where, if we would need to do basically heat steam or something like that, we would need an intermediate heat exchanger of some sort. So we're designing for not needing that with the power conversion system, but if we're heating water or some sort of process fluid, we would need a separate intermediate heat exchanger. Also, if we're capturing the waste heat from the Brayton cycle, we would need a heat exchanger for that.
Makes sense. Thanks. And we have a follow-up question as well, which is, does the passive core cooling jacket assume that all the heat pipes are not credited? I hope I'm capturing that correctly.
Yeah, so Vefa, maybe help me out there, but I think we postulate 4 failed heat pipes in an accident scenario.
Yeah, in a heat pipe failure scenario, I think the core is strong enough to survive and continue operation. Actually, I think it's about 3 heat pipes. That's the design goal. Yeah, the passive cooling system will remove the decay heat, assuming that the core is able to successfully shut down or tripped.
Mm-hmm. And as temperatures increase, reactivity of this reactor also decreases.
We have a very strong fuel temperature feedback. The Doppler feedback is the dominant feedback effect. So any reactivity insertion accident scenario, the power will go up initially. With that, the fuel temperature will go up and immediately turn the power peak basically down until you hit the signal to trip the reactor, right? Yeah, and that will we design such that the amount of reactivity insertion is limited, so that your temperature increase is going to be limited, not challenge your heat pipes, the fuel, or the core block.
Thank you. And we have another question in the chat, which is, regarding loading following, is the response time limited by the reactor core system or the heat removal cycle?
Yeah, so I'll start with we're able to load follow at millisecond ranges through the addition of a small battery bank. So the reactor itself cannot load follow and stay on basically in millisecond ranges, but basically we use a battery to cushion that load change. But we know in some instances where we're off grid and we're not supported by the large 60 hertz grid backing the frequency, etc., we'll need to be able to move with a mine, for instance, may turn on a piece of equipment or turn off a piece of equipment. So that's our primary for if we need extremely fast load following. That's our method. If we're talking just normal ramping, I'll defer to Vefa on that one. I think I know the answer, but I don't want to misspeak.
No, I think if we are talking about just nuclear load follow, I think minutes, 15 minutes, half hour, or maybe a couple hours. We haven't finalized the design yet on that, but in a previous design iteration, we were targeting 15 minutes actually. That was for some special applications.
Yeah, and it's just a relatively small reactor. So load following of massive pressurized water reactors, right? That's a challenge. But really, I think we're limited, Vefa, by the just the remaining heat. Basically, there's such a large heat sink of the core and all the metal. I think that's what we're limited on speed from
Right.
Coming down on load. Is that correct?
That's correct. Yeah.
Yeah. Oh, Ben, I think you're on mute.
Yeah, thank you. A few more questions in the chat. Could you comment on what the exit temperature is from a Brayton cycle, i.e. what temperature is available for the waste heat?
I think it's around 150 C, maybe 200 C actually. It's somewhere in that range. Can you confirm?
I think that's correct. Yeah. I
So,
remember the average temperature being 640 or something like that. So yeah, the exit is at that range.
Yep.
Okay, thanks. And the next one is the core structure graphite between the Triso Fuel compacts and the heat pipes?
Yep. That's correct.
Yeah, we have a solid core block of graphite channels in the graphite block, which includes the heat pipes and the Triso compacts. Yes.
And do you also use graphite for the reflector?
Yes.
Yeah. Thanks.
Yes, we did a lot of work to ensure we could use graphite versus some more exotic and also potentially toxic materials. Especially
Like beryllium, I guess.
That was
Yes,
beryllium was under consideration, but we worked our way through that.
Beryllium helps a lot, obviously, to keep the size down, but it's very difficult to handle. So graphite would be the best choice.
Do you control it using drums in the reflector?
We have control drums in the reflector, and those drums are mainly to compensate for depletion, load follow, and also shutdown. And we have diverse and redundant shutdown systems. We also have control rods in the core for redundancy to shut down. There is another concern with respect to transportation. You have to assume the worst case scenario in a transportation accident where you drop this core in a body of water and there's water ingress and it can go critical. So you have to take into account those considerations. So we have additional control rods set aside for transportation purposes as well.
Okay, so it's transported with the core as a solid block rather than in pieces.
That's correct. Yeah, it's factory fueled, just like the pictures that Mike showed, and transported from the factory to the site with the fuel inside.
And we have more questions coming in. What is the design specification for interfacial heat transfer resistance or coefficient between the heat pipe and the graphite monolithic solid core?
Good question. I don't know the exact, I don't know the numbers on that, but I know where that question is driving at is that how effective is that heat transfer and are we using some sort of medium between the two?
We're using...
I'll defer to Vefa on that.
Okay, so we're using helium. So the core block is in a helium atmosphere. Helium heat transfer coefficient is not too bad. I think it's it has one of the best conductivity among the other inert gases, I believe. So it's all helium. All our design calculations and safety analysis calculations assume a full size gap between the fuel and the graphite block for conservatism. But I think the gaps are the largest resistance, thermal resistance in the modeling and analysis area. So yeah, I think the other assumption is that core block is not a mono block. It has, as Mike showed, it's composed of unit cells, like unit fuel assemblies, and we also assume gaps between those unit cells. So that's another component of the thermal resistance that we consider.
Thanks. So I did have a question. I've just blanked on the question. Give me a second. It'll come back to me. Does anybody else have any questions while I'm trying to remember mine?
Yeah, I would like to hear a little bit more about your spent fuel storage plan. Are you planning to bring all the fuel back to the same site where you're constructing and fueling the reactors? Or are you hoping to have a bunch of smaller sites? Or I'd just like to hear more about that. Thanks.
Yeah, we're planning on bringing it back to the same site where the reactors are being fueled and refueled. It's simpler from a license perspective. I think there could be, given that we're looking at markets in both the US and Canada, we may need more than one facility. We may manufacture all the units in one country, but have a fuel storage site in each country. But our primary goal is for the manufacturing and refueling facility also to be the storage for the spent fuel. We're also looking at the actual reactor container and its shipping container as being the cask for long-term storage once the reactor has reached its useful life. But, you know, US and Canada also have some differences. You know, you have to think about whether either country will eventually get to a geological storage for the long-term storage, but certainly our quote-unquote short-term storage would be at the factory. And waste, right? You know, I know it's a key topic for nuclear, but waste volumes are, you know, this is a very small reactor, so we're dealing with quite small overall waste volumes.
Yeah, you already answered my.
Yeah, go ahead.
I was saying you answered my follow-up. I could imagine just some sort of like political hurdles of the view of like if you only had one storage site and Canada would have to send their fuel back to the US. I can imagine that some people would be quite upset about that. But you mentioned that you're looking at having two sites, so thanks for touching on that.
Very astute and excellent question, and that is exactly why we're looking at two different locations, is the political view of fuel, spent fuel crossing the border. I mean, that's really what it comes down to, honestly.
Just as a comparison, the amount of uranium in the eVinci reactor is basically almost equal to the amount of uranium in a single PWR fuel assembly. So the amount of waste or used fuel is going to be, you know, small in comparison as well.
So this is Paul Wilson. Just to follow up on that, it'll be small in comparison to a PWR, but what's the burnup anticipated for the fuel?
Right. For this latest design, it's going to be small with the Triso Fuel. I think for 4.5 or 5 year operation time at 15 megawatt thermal, I think we get up to 45,000 megawatt days per MTU. So it's not that small, but it's obviously smaller than the light water reactor fuel. Right,
but so from a amount of waste per unit of energy produced, you're not very different from a light water reactor, right? And so the quantity of fuel per reactor is small, but per unit of energy provided to the consumer, you're going to be very similar scale to a light water reactor. And if you have, in the ideal world where you sell thousands of these things, then the waste volumes will add up as well, right?
Yes, that's correct. You know, it certainly is an important topic, but but also the overall volumes of waste for the entire U.S. nuclear fleet's operating history is relatively small.
Absolutely, yeah, agreed. But
So you know, it's all in whatever lens you're viewing the volume of waste being. But you're right. Thousands of reactors could lead to similar volumes as PWR operating fleet over time. But I think most reactors, unless they're really trying to close off a fuel cycle, would have a similar situation. And
yep.
you know, I used to work at a fossil plant where we filled an entire reservoir with coal ash in a fairly short period of time. So, you know, when we talk about waste volumes and energy, you know, this is just a topic I get a little, you know, it has to be put into context with other sources as well. But I understand.
So following up to that, another hurdle that arises when you do storage away from the reactor is that now your construction or your refueling facility has to be sited. Even if a reactor is not there, it's going to take fuel from a bunch of different places. Are you sort of preparing for the sort of political challenges of the same sort of things that waste control specialists and Holtec are dealing with sort of a public outcry of we don't want to take fuel that's producing energy somewhere else in the country? How are you thinking of those challenges when I don't know if you already have a site for your plant or not, but.
Yeah, so we have not defined our final sites in US or Canada for waste storage and spent fuel storage. You know, will there be some political, resistance no matter where we go? Most likely. But there are certainly areas that are much more, I'll say, understanding of what the realities of spent fuel storage are, right? Including nuclear operating plants in the U.S. Even though it's not spent fuel, Westinghouse's fuel facility in Colombia, we make PWR fuel there and BWR, but primarily PWR fuel there. There are the populace sometimes challenges that usually very small percentage of the people that are, quite loud, honestly, at sometimes. But overwhelmingly, the economic support to that community is quite substantial from that fuel facility. So, when we actually look at there is an overwhelming positive view of having a facility like that on site. But you're right, there would be challenges citing an initial one. But there's definitely some areas in both Canada and the U.S. that we feel it's feasible. And also, there are defense and other fuel storage areas in the country as well that basically operate with very little concern.
Could I just ask a follow-up question to some of the questions you've had around sort of fuel mass? So the reactor's operating at 45 gigawatt days per ton-ish. Presumably that's constrained by the operating lifetime of 5 years rather than something else. And then to what extent is the reactor size and core mass limited by thermal power density versus fuel critical mass sort of constraints?
Yeah, it's a delicate balance. Reactor physics plays a big role in designing this core. You're limited by size. You want to be transportable to be able to fit this on a truck. So you have size considerations, and you want to be able to produce a certain amount of power and last for a certain amount of period. But then you want to have, as much fuel as possible and have excess reactivity to take you that many years. So you start, doing some optioneering studies, basically looking at your web thickness in the core block, which is mainly your moderator, and you change your fuel to moderator ratios. Look at how much excess reactivity you have, that will get you, say, 5 years, right? However, too much excess reactivity is kind of dangerous. You want to be able to control that excess reactivity. You want to have enough controlled run worth to be able to address any reactivity insertion accidents. So you need to be able to use some burnable absorbers to keep that initial excess reactivity down. So it's a lot of challenging work. Design activities going into the core design, which is driving the rest of the reactor actually. I don't know if did that make did that answer your question or concern?
Yeah, I think so. I think you're saying that because it could be limited from a thermal perspective, right? It could be that there's only so much power you can get out of the block before the transient becomes too limiting. But it sounds like the size of the reactor has to be this big in order to, otherwise you can't get it critical.
That's right. And there is within to be able to fit in that envelope, you have a certain number of heat pipes that you can include in the core, right? And each heat pipe has a limit, thermal limit. You cannot operate beyond that limit to, challenge some of these heat pipe phenomena like sonic limits or boiling limits or etc. So, yeah, these are the constraints that we have to take care of, basically.
Right. Okay. Yeah. Thanks. That makes sense. And
I guess spending a lot of time working to optimize this core design with commercial inputs and all. This is kind of where we are actually right now of making our final tweaks for refueling life, total power output, size. The concept itself we're quite clear on, but we're really in that phase that you're describing right now of finalizing what is our final answer on the core.
Right.
I mean, that's exactly where we are right now.
And to what extent does this affect the economics? Is the fuel load a significant portion of the overall cost of the unit?
Yeah. So economics. We've been looking at all sorts of models, right? LCOE models with all sorts of models around the different components of the cost for the reactor. The fuel, especially with a UCO Triso, is going to be a significant portion of the cost. We're actually looking at what next generation of the technology after our first units out the door, what fuel will it use? Because we would like to come down the cost curve in the future with something that's got a higher density and a lower cost than UCO Triso as it exists today. But we are working towards the demonstration, planning on UCO Triso because of its regulatory acceptance and some things like that. But we're certainly not ruling out in the future going to a lower cost fuel so we can open up the market more. But the fuel itself is a fairly substantial component of the cost right now. And even there's some uncertainty too, as the supply chain for high assay low enriched uranium is not real clear right now. So that the actual enrichment up to the 19.75%, there's some big assumptions around cost there. But as far as UCO Triso manufacturer, we have some fairly reasonable ideas of cost based on actual proposals from the fuel manufacturers. But it's a big percentage. And I don't get into details of those numbers. That's more in an NDA type, forum. We have this, very detailed of every component cost for the reactor. And the resulting LCOE is, like as I've said, is less than some of the areas where diesel is being transported at distance in Canada and Alaska.
That makes sense. Thank you. I could ask many follow-up questions on that, but I shouldn't monopolize this. So I have okay, so there was a couple of others from the chat. There's one on, can you say anything about anticipated operational and security staff? I think you mentioned this earlier, but if there's anything to say on that.
Yeah, so we're planning a full-time operator, basically 24/7 operator on site right now. And we can have more than one unit per operator. We are planning, in some instances, we will be able to take credit for the existing security force. So for instance, most mine sites that we've talked to they have a security force that we believe could be credited. If it goes to a true remote community, no police force, nothing, we would likely need an armed security individual as well. So we're building that into our economic models, even though realistically we believe no operator. We could foresee a time where no operator would be required, but we have to go because we like to go conservative on our economic model. I feel there's others out there that are going very aggressive on their economic model, and I think that leads to you make promises that you can't keep in the end.
Makes sense. And with some of these mines, what sort of payback time for the reactor is there? And do the mines operate for long enough to make it worthwhile? / can you ship the reactor around if needed?
Yeah, so payback time, right? So one of the key aspects of LCOE is the actual cost of capital that's assumed. So, nuclear obviously has a higher capital cost than diesel, but then the fuel cost for diesel in some of these areas is just extraordinarily high. So, there's diesel LCOEs at some of these mines that are, $300, $400, $500, even $600 per megawatt hour, which are, we can certainly come in lower than many of those areas. So it's really, when you look at payback, the payback can be quite fast, based upon someone's going, like the mining sites have to get financing for the reactor. And we've assumed pretty high cost of capital since it's a nascent technology versus the cost of capital for something like solar that's now been very well and deployed and has a long history. So, we've been assuming 6 to 10% for cost of capital, which is quite high. And our overall LCOE still can come in below the diesel numbers. So, we think the payback is actually quite fast. And then there's also ancillary benefits of, potentially getting some of these sites completely off of fuel shipments. One of their big risks is if they miss a fuel shipment, they basically can't operate and they have to evacuate the site because of the temperatures. So there's some real benefit to the resiliency that's hard to quantify in cost, because it's really it's avoidance of risk, which can be quantified in cost, but we're actually talking with some mines about that now. The payback's pretty quick for an area that's $300, $400, $500, $600 a megawatt hour.
Yeah, I can imagine actually. Yeah, when you big quote that high, yes, and the payback's can be really quick. No, that's interesting. I think
Canada's also starting to put a carbon tax on as well. So there's some things like that when you look at those costs in the future, it's escalating. And diesel costs in Canada and the U.S. and those remote areas have been escalating quite quickly. So it's, as you look out 4 or 5 years and presuming those escalations continue, some of those sites could be 600-700 megawatt hour fairly quickly.
It makes sense. And we have one more in the chat, which is taking us back to a technical question. Are you allowed to say what is the average heat pipe thermal load?
So I would say no, but we've done some benchmarking and discussions with labs as well as some commercial heat pipe users. I believe our heat pipes are actually substantially more capable than existing heat pipes right now. So the reason I'm not going to answer this question is it's a key advantage we believe we have from a technology perspective. There is another heat pipe reactor company out there right now, and more companies are starting to look at heat pipes as a viable or even their primary path. So, Westinghouse, we're quite sensitive to maintaining our lead in this space as really the only nuclear safety-related heat pipe manufacturer that we know exists right now. And the performance, we believe, is also, again, substantially higher than others out in the world right now. it helps us with our size, obviously.
Thank you. That's interesting. That's interesting stuff.
Yeah.
Okay, we've managed half an hour of questions, which is definitely a record for this year, but at least as I'm aware, or can remember. So it shows how much interest we have. Does anybody have any final questions, or shall we give Mike and Vepa a break? It looks like you finally get to take your lunch break if you haven't already. Well earned. Thank you again. If everyone could please, thank the speaker. The speakers, we would be clapping if you were here in person. As it is, you can just assume we're all clapping. I'm sure we are. Yeah, that's very interesting, and we look forward to engaging with you further around eVinci.
Yeah, and we'll be happy to come back as we proceed with the technology. I think there'll be some big milestones over the next year or so. And, feel free to reach out to us on, any form that you like. So I'll send the slides out to you, Ben, so you can distribute to the team. And I'll actually just apply my contact information to that as well, that you can distribute.
Thank you very much. I'll circulate those.